Today our seminar speaker is Dr. Larry Aagesen. He's a computational scientist at Idaho National Laboratory. He's the leader of the computational microstructure science group there. His primary area of expertise is in the phase field method, having developed phase field models for a variety of physical phenomena, including fission gas bubble evolution, solid state precipitation, and a variety of other phenomena. He's also my former group mate at INL as well. So join me in thanking Larry for coming.
Yeah, well, thank you very much for the introduction, Ben, and thank you again for the invitation. It's my pleasure to be here. I thought I'd start out before getting into the technical part of the talk, just to say a little bit about INL. A few former INL folks are here, but it may not be as familiar to everyone in the audience. So just thought I'd say a little bit about what we do and why. So, you know, climate change being a very pressing concern for our planet. A lot of people, including myself, think that nuclear energy should be an important part of the strategy to address that by reducing carbon emissions. So recently, a group of utilities that are members of the Nuclear Energy Institute identified the need to add up to 100 gigawatts of nuclear power generating capability by 2050, which would be more than double the current capacity. And so in order to achieve that kind of an increase, it's going to require effort by a significant number of players. And so Idaho National Lab, being the lead lab in the Department of Energy complex for commercial energy, this is a major area of focus for us. So our mission, I'll just read it from the screen, is to discover, demonstrate, and secure innovative nuclear energy solutions, clean energy options, and critical infrastructure. So we do that through the work of 5 different directorates that are shown up here. So nuclear science and technology, where I work. The advanced test reactor and materials and fuels complex is where a lot of kind of the rubber meets the road, where nuclear experiments get run and characterization after those experiments take place. So those are, most of those facilities are out on the desert site. We also have an energy and environmental science and technology, which does a lot of energy related research, including things like looking at the performance of batteries for electric vehicles. And then we have the National Homeland Security Science and Technology Directorate, which focuses on critical infrastructure, things like our electric grid and Wi-Fi networks, things like that. So just to kind of show how that those different missionary works are broken up, I just wanted to give a few statistics. So INL is the 5th largest Department of Energy national lab. And so in terms of operating budget, we're about $1.6 billion annually with about 5,500 full-time employees. So then if you look at the breakdown of where we spend our money, which is roughly equivalent to our time, we have about just over half of our work is toward energy related work. And you know, the bulk of that is from the Office of Nuclear Energy within DOE. About a third of our work is national security related. And then the remaining about 16% comes from a variety of other sources. So in terms of the work that we're doing in the nuclear space, we're kind of focused both on sustaining the existing commercial fleet and allowing them to improve, and then also expanding the development and licensing and deployment of new reactor types. So we do that in areas from the existing commercial fleet, looking at things like human factors research and how do we make existing plants operations safer, to all the way to looking at the evolution of microstructure in UO2 fuel that's used in current commercial plants, and trying to help understand how utilities can build a licensing case and go to increase burnup so that they can operate more economically. And then all the way to looking at advanced nuclear technologies, so things like the designs and the regulatory frameworks for new types of plants, as well as the critically important questions about fuels and materials for those types of plants. So as far as advanced reactors, this is just kind of a snapshot of several of the oncoming new projects, new reactors that are going to be deployed within the next half dozen years or so, that INL has some involvement with. Many of these are cited at INL, not all of them, but many projects here. I think this is a really exciting time to be involved in nuclear. And so one of the things that is both exciting but also a little bit challenging is that many of these new reactor designs are very different from the commercial light water reactor fleet that we have a lot of data on. So in order to try to, so we don't have a lot of data for some of these new reactor types. New data is expensive, it's time consuming to get. So to kind of try to help address that challenge, a lot of folks that are involved with the reactors, including INL, are turning to modeling and simulation. So at INL, a lot of the modeling and simulation tools that we're using are developed on top of this platform called MOOS, which stands for Multiphysics Object-Oriented Simulation Environment. So MOOS is a general purpose open source framework for solving partial differential equations. It's predominantly a finite element based framework or code. We do have some capabilities to do finite volume, but it's primarily a finite element. And so MOOS, the framework itself, has implemented many of the things that are needed to run large, computationally expensive, complex problems efficiently. A lot of that's already implemented. So folks that are interested in physics and design can focus on that while allowing the framework to handle things like implicit time integration, time step adaptivity, and mesh adaptivity have been built into the framework. We also have a lot of capability for parallelization, both using MPI parallelization and multi-threading. That allows us to run efficiently on large-scale computers to attack big problems. Also have some other capabilities, things like automatic differentiation, which is important for implicit time step problems, using the scheme that we use. And then the code has a lot of flexibility. It's agnostic to dimension, parallelization, finite element shape functions that you might use. So basically allows the folks that are trying to write equations and solve them to focus on that part of it, while a lot of the underlying work is already taken care of. So just to say a little bit more about how the framework is constructed. So MOOS itself sits on top of a couple layers of existing codes or frameworks. So we use PETSI as our primary numerical solver. So that's kind of underlying how we solve the matrix vector problem that results from the finite element discretization. And then we use the libmesh framework to handle kind of a lot of the lower level things that are needed for the finite element methods, such as mesh generation, input output, and so on. And then MOOS kind of sits on top of libmesh, and basically we take the physics problem that we want to solve, we put it in the weak form of the partial differential equation in the weak form, and then use MOOS to solve it. And so there's a couple different ways physics are implemented in MOOS. I mean, the implementation is the same, but the way you would get access to them is just a little different. So we have many physics modules that are included in the open source distribution. So if you go to moosframework.org and download it, you will get all of these. So if you can see that, yeah. So we've got things like mechanics, phase field modeling, which is primarily what I do, heat conduction, chemical reaction. All of that is kind of generic material parameters, but the code itself is very capable of solving the physics with the parameterization that you need. So that's all included with open source Moose. We also have other open source applications, so you can get that from, you can get applications like that from GitHub, again, download for free. So an example of that is Malamute. So that's an application that's geared towards advanced manufacturing processes built on top of the Moose framework. So you can either install Moose first and then get that, or you can install Malamute first and it'll bring in Moose as a submodule. And then finally, we have applications that a license is required for. So those are things where we have a lot of nuclear specific type material properties and things built in, where we wouldn't necessarily want to like release that to the whole internet for anyone to use. So those applications such as Marmot and Bison have a lot of nuclear specific capabilities. So Marmot is the phase field, basically the module that does phase field on nuclear materials. And then Bison is the application that we use to simulate the performance of a fuel element kind of at the engineering scale or at the design scale. So those are the types of things that you would need a license for. Using that Bison tool, Bison is what we use primarily as our code for looking at the performance of a nuclear fuel element. So this is kind of what's going to be of interest to a designer. Bison was developed, originally looking at the performance of traditional UO2 with zirconium cladding. And so for that type of problem, there's a lot of empirical data for material properties and material properties and other parameters you would need to run the simulations. They're available from, the many years of historical data that we have for light water reactors. But for many of these new reactor designs, we just don't have, the historical data. And like I said earlier, it's very expensive and time consuming to obtain. So for a lot of these new reactor types, we're moving towards using a multi-scale modeling approach to try to inform Bison. And so that can be a combination of atomistic and mesoscale methods. So atomistic methods sometimes are used directly as we perform an atomistic calculation, maybe pass that directly to Bison. Oftentimes, though, we need to account for what's happening at the microstructure, because the microstructure can have an important impact on the fuel performance. So we use Marmot, which, as I mentioned in the last slide, is our Moose-based application for microstructural evolution in nuclear materials. And so bringing together the first principles and molecular dynamics techniques, passing that to Marmot to parameterize the model, and then developing some kind of either analytical model or either from curve fit or from like a physics-based model that's parameterized, passing that into Bison for field performance simulations. So that's kind of the framework that we're using, and I want to now kind of give a couple specific examples of this kind of multi-scale approach and kind of how we're bringing that to better understand the performance of fuels. So the first example I want to give is in metallic uranium zirconium fuels, which sometimes in the past have been mixed in with some plutonium. So that's kind of why that's in parentheses there. So this type of fuel is of interest to several new reactor designs, such as the TerraPower Natrium, which is going to be sited in Wyoming, the Oklo Aurora, as well as Lightbridge. And so we do have some experience with this type of fuel from the EBR2 reactor at INL. And so one of the things that we know based on this experience is that this fuel swells a lot. And so that's a major performance consideration with this fuel. So swelling, coming into contact and potentially damaging the cladding as it does so, it's very important to understand. We also know from the historical experience a bit about the microstructure and how that evolves under radiation. So in the center of the fuel, where it's hotter, it's predominantly the gamma phase with some alpha or beta mixed in. And so in that gamma dominated phase, we see the fission gas bubbles that form tend to be quite large and kind of spherical. And then also shown some later micrographs that they tend to interconnect as they grow. In the periphery of the fuel, where it's not so hot, the alpha phase is dominant, and there's some delta phase mixed in. The swelling mechanism is primarily due to grain boundary tearing. Doesn't swell quite as bad, but the swelling behavior is predominantly controlled by this gamma phase material. So the Bison models currently assume that the swelling fission gas release is dominated by this gamma phase mechanism throughout. So we have a few different models that have relatively recently been added to Bison for this type of fuel. So we have this gaseous swelling model, which basically makes some simplifying assumptions about the physics of the bubble growth that allows us to reduce things to a single analytical model that's dependent on some parameters, not all of which are very well known, but at least it gives us a good starting point. So that expression that I showed before gives the swelling as a function of the fission density. What eventually happens is, as the fuel starts to swell enough, it becomes interconnected, and then as the interconnection happens, interconnection to surface allows the fission gas within the fuel to be released from the fuel pin itself, and so the model assumes that kind of happens in linearly in a regime from an interconnecting initiating porosity to a terminating porosity. And so as that swelling occurs, we also, the model sort of assumes that the fraction of gas release also kind of tapers off in that same range. So we had some previous assumptions on what the values for that interconnecting and initiating and terminating porosity were, but they weren't really very well physically grounded. And one of the values was actually chosen more based on how to make the model actually run well. So what we tried to do in this work is to try to develop improved estimates of those parameters for the model by doing simulations of interconnection and percolation of gas bubbles. So to do that, we needed to run some pretty large 3D simulations. So we're using a relatively simple model for this. It's a Cahn-Hilliard model, and we have basically a single defect species that represents the gas atoms found with vacancies. And it uses a double well function for the free energy, which basically gives us normalized concentrations of defects of 0, which is basically the fuel, and 1, which is the bubble phase. Then we have another contribution to the energy, this grad, this gradient term that basically results from the interfacial energy, or represents the interfacial energy between the bubble and the matrix phase. And so we have kind of a diffusion type equation here with a source term that represents the production of these fission gas atoms. So I'll talk next about how we actually did these simulations with that model. So we needed some initial conditions. Phase field does not handle nucleation in a natural way. So generally we have to assume some starting condition for the initial bubble density. So we did have some experiments that we could use to parameterize that. And so we basically populated a bubble, a set of bubbles based on this experimentally known bubble distribution at a relatively early burnup, and used that as our initial conditions. Through work that I did in collaboration with Professor Beeler there, we did know that the interfacial energy was 1.8 joules per meter squared. So that's an important parameter for materials that was not really very well known until his work. Another parameter that was not well known at the time was the diffusivity of the defect species. So we actually just we can figure out what the source strength is based on the fission rate, and then we varied the diffusivity parametrically to see what the effect was on morphology. So this just kind of shows some snapshots of the microstructure evolution. So you start out with these isolated gas bubbles. They start to grow, and then as they grow, they start to kind of impinge on one another, and you start to see some kind of like interconnected channels between them, and eventually those interconnected channels get large enough that they connect one side of the microstructure to the other. As I said before, we looked at the effect of diffusivity parametrically. So one thing that you see from that is that if you increase the diffusivity by a factor of 5, the size scale of the microstructure actually changes quite noticeably. So the microstructure becomes coarser, and that's due to the effect of the surface energy. The system wants to reduce its surface energy, and it can do so more quickly when it has a higher diffusivity. So that's one thing that we wanted to understand the effect of on field performance, which I'll come back to briefly. First, though, to kind of try to understand how we're going to link this to engineering scale simulations, I wanted to say how we're kind of characterizing the connectivity. So what we did was we ran these simulations, and then we have a tool within Moose that allows us basically to identify whether a given bubble is connected to a surface or not. So we picked a surface. We use that algorithm to say, okay, what volume fraction of the bubbles is actually connected to that surface? And that allowed us to generate plots such as these. And we did that for multiple different configurations. So that's one measure of the interconnectivity. Another measure that we looked at was the percolation. So percolation basically is do we have a single bubble that connects one side of the microstructure to the other? So these two faces across, are they connected by a single bubble? That's the percolation threshold. So we looked at the percolation threshold for different diffusivities. And you see that there's some variation, but it's pretty small, and it actually it's not really a consistent trend with the microstructure, with the diffusivity. So really, what that says is that it's the diffusivity, even though the size scale of the microstructure is changing quite a bit, the percolation threshold is pretty insensitive to that. So that gives us kind of confidence in our methodology. The other thing that we looked at was just developing different plots of this, different plots of this interconnectivity function, or this fraction vented function, as for different values of diffusivity. Then trying to calculate an average based on those many configurations of what is the mean value of the percolation threshold. So, again, we're trying to connect this to engineering scale field performance. So how do we do that? So in order for the fuel to get released, there has to be a connected path from the center of these pins to the exterior surfaces. So we assume that no significant amount of gas can be released until we reach that value of the percolation threshold. So we picked what we thought was the most reasonable number for the percolation threshold, and set that as our initial interconnecting initiation porosity. So the P sub I was based on the percolation threshold. And then we also know from some other PIE data, radiation examination data, that the fission gas release plateaued at about 80% of the fission gas that was produced. So we defined a new porosity P0.8 as the porosity at which the fraction vented is equal to 0.8. And then based on that PIE data, we said, okay, terminating porosity is when we reach that porosity where the fraction vented is 0.8. And so that turned out to be a value of 0.28. So those are basically the numbers that we were looking for from our microstructure level simulations. And then going back to that model that I initially talked about for swelling. Okay, so now we have the P sub I and the P sub T. And so previously, we had one of my colleagues, Al Casagrande, who's now at TerraPower, he had done this optimization strategy using Dakota, where he took all of the parameters in that model that I showed in the beginning of this section and did a bunch of did Dakota optimization to figure out what are the most reasonable numbers that fit the data that we have. And one of the things he found in doing that was that the values that he got were very sensitive to the initial guesses that he gave for things like the initial guesses that he gave for those parameters. So if you see, like, starting out with two different numbers for the initial bubble number density, he ended up getting very different results from the Dakota optimization, and also got the initiating porosity and terminating porosity. He got very different results from those. So what we did then instead was to sorry, I was actually pointing at the wrong figures there. Those are the initiating and terminating porosities. So moving to now having better estimates of those values from the microstructure level simulations, we could hold those values as fixed and then allow Dakota optimization to fit the remainder of the parameters. And we found that the resulting numbers were actually much less sensitive to the value of the initial guess, and we got a pretty good, we got a pretty consistent set of numbers based on regardless of where we set the initial value. So I think that shows that we can use these mesoscale simulations to kind of reduce uncertainty and help improve our knowledge of other parameters that are not so easy to measure by using this mesoscale work. So I want to kind of change to a different topic within the same area of metallic fuels. So moving on to fuel cladding chemical interaction. This we also know from the EBR2 data is another major performance limitation for used fuels. And so FCCI, it's a really complex set of chemical interaction that result from interactions or interdiffusion between the fuel constituents and the cladding constituents. The cladding that was historically used in EBR2 is various types of steels, most commonly a steel grade called HT9, which has a BCC crystal structure. So on the fuel side, we can have diffusion of iron into the uranium that can result in a low melting temperature eutectic. On the cladding side, we see diffusion, particularly of the lanthanide fission products from the fuel into the cladding, and that leads to the formation of a couple different types of brittle intermetallic phases, which are kind of commonly called wastage. The most prevalent of those intermetallics is this Fe17 Nd2. So sometimes you see some chromium in that, as well as some cerium. And so this brittle phase really degrades the cladding mechanical properties. And so what we're trying to do is to come up with a more mechanistic approach to understanding that. So to understand the physics, we kind of look at the progress of this as a multi-step process where the lanthanides are created in the fuel. The lanthanides that are of concern are listed by prevalence there, starting with neodymium, cerium, and so on down the line. So they're created in the fuel as fission products, according to their fission yield. Then they're transported to the edge of the pin, and then depending on whether these fields are swelling, and so depending on whether the fuel is in contact or not, depends on that controls how they're transported into the cladding. EBR2 fuel had liquid sodium in between the fuel and the cladding, so before contact, it would diffuse through the liquid sodium. After contact, it just directly goes across the fuel. But in any case, that step we don't think is that important because the transport is fast either way. Liquid sodium, transport through liquid sodium is fast. Direct contact is also fast. So that's probably not the limiting step. And so, as I said, this Fe17 neodymium 2 phase is kind of the most prevalent one that's been observed. And so there has been some data that would suggest that the thickness of the growth proceeds with this parabolic growth law. But that was from diffusion coupled data, so that's kind of what we have to go on now, but we know that it could actually, the kinetics may actually end up being different. But with all that information, then we started working on developing a mechanistic model for FCCI growth. And so there is an existing empirical model in Bison based on the EBR2 data. But again, that's all based on just one set of reactor operating conditions. There's many new types of designs that are being considered, and so that empirical model may not be extensible. So that's why we're developing this more mechanistic approach. And so the basic idea is that we want to calculate the diffusion. We're initially focusing just on neodymium because it's the most prevalent species. We want to calculate its production. Its transport through effective diffusion. We also account for the decay with this lambda C term. And so that allows us to figure out how fast it's getting to the edge of the fuel pin. Then we want to calculate how fast this intermetallic is growing. And we from that diffusion coupled data, we think it's a growth law of this form. Initial data would suggest that this factor of alpha is a half, but we actually wrote the code kind of agnostic to that number so that we could change that flexibly as needed. And then with that calculated thickness, then we pass that to this model of cladding degradation that was already implemented by collaborators at Argonne National Lab that kind of thins out the cladding it kind of thins out the cladding based on this growth of this intermetallic layer. So one of the most important things in understanding transport is figuring out what is the effective diffusivity of these lanthanides through the fuel. So in order to do that, we need to account for the fuel microstructure, which is very complicated. So we start out with isolated porosity, and then as burnup increases, and I'm sorry, I noticed as I was looking at this before that this is a typo. I think this is actually like 2.2% burnup. So as we get to higher burnup, the fuel becomes interconnected. And then for this EBR2 fuel and for many other designs such as natrium, they're still planning on having the liquid sodium. So the liquid sodium can actually then infiltrate this interconnected porosity. So there's kind of three phases that we need to consider and be able to understand each phase's effect on the effective diffusivity. And then to determine how each of those phases, we need to also know the diffusivity through the bulk of the fuel, the surface diffusivity, and the liquid sodium. So I'll talk first about those diffusivities. This was primarily done by my colleague Chao Zhang. So he's basically assuming that the alpha phase is the phase that's most, that's actually where the temperature is lowest, so that's actually going to control the kinetics of diffusivity. So he used a nudged elastic band method to calculate the energy barriers for the various diffusion pathways of neodymium through the solid uranium fuel. And then with those energy barriers, then ran kinetic Monte Carlo calculations to get diffusivity in all three crystallographic directions. And then we did a polycrystalline average of those, which is what's actually shown up here. For the surface diffusivity, Chao applied the same methodology, but just applied it to a particular surface of the alpha U fuel. And then for the liquid sodium, we were able to take advantage of some previous calculations that were done in the literature using ab initio molecular dynamics. Okay, so those are the input values to our mesoscale simulations, where we actually then want to figure out an effective diffusivity that accounts for the microstructure. So as I said, the first phase of that is this isolated porosity. We have high diffusivity on the pore surfaces. So even though there's a sort of a hole there, which would reduce the diffusivity, you actually then have a high diffusivity surface that could result in an overall increase in the effective diffusivity. So we looked at a model effective transport, which was actually developed for heat transfer, called the Maxwell-Yukin model. So if the diffusivity in the spherical inclusions is much higher than that in the matrix, it actually reduces to a form that's dependent only on the volume fraction of the spherical inclusions. And so we hypothesized that this expression might still be valid as long as the surface diffusivity is significantly greater than the bulk diffusivity, which it normally is. So in order to test this hypothesis out, we used some tools in the Moose framework known as the asymptotic expansion homogenization method. And we looked at the effective diffusivity of both isolated isolated pores with high bulk diffusivity, as well as isolated pores with high surface diffusivity. And we found that the Maxwell-Yukin expression worked just about as well, particularly at low volume fractions, which is really most relevant before interconnection begins anyways. So based on that, we felt confident to use the Maxwell-Yukin model for that first case of isolated porosity. The next case that we're looking at is effective diffusivity through interconnected porosity without sodium infiltration. So we used those previous simulations that I mentioned. We were able to use those again and figure out what is the effective diffusivity through those microstructures. So again, using this AEH technique, we could look at the effective diffusivity as a function of the porosity and also for varying surface diffusivities. And so by using a lot of batch processing, we were able to kind of crunch a lot of data for a pretty wide range of surface diffusivities from about 10 to the 6 to 10 to the 9 times greater than the bulk diffusivities, and also looking at a very wide range of porosities. And so we found, you can't see it super well from these, but we did find that we matched the Maxwell-Yukin model well at low porosities. Which is good. It kind of validates what we were assuming previously. But then we also developed this function that the red line to fit to the data that kind of accounts for the interconnectivity, and I think captures the data well over a pretty wide range of porosities. So the final step, that was for interconnection without sodium infiltration. The final step was for when sodium gets into that interconnected porosity. That happens when it starts when the porosity is above about 0.26. And so the sodium, as I said before, is the neodymium diffuses much more quickly through the sodium than through the bulk. And so when the structure becomes fully interconnected, it becomes what's known as a bicontinuous structure. So that's a structure where both phases are completely percolated from one side to the other. So there's been some past work that's shown that when in a bicontinuous structure, when the diffusivity of one phase is much larger than another, such as the case here with the high diffusivity sodium, then the effective diffusivity is well represented by this expression, which is basically the diffusivity of the high diffusivity phase times the porosity over a factor called the tortuosity tau. And that's been shown to be about equal to 1.5 for a wide range of these bicontinuous structures. So we use that. We didn't try to run any new calculations ourselves. Yeah, so basically putting all that together, we have a function now that kind of captures the effects of these three different stages of interconnection, and that's been implemented in a Bison model. That's what's shown here. All this typewriter font text. So that's been implemented in Bison, and then now for validation, we've started to do some work looking at the X447 assessment case from the EBR2 reactor. We looked at this assessment case, and basically, like, one of the unknowns that we still have here is this prefactor for the growth rate. Like I said, we're assuming that the growth constant is 1/2, but we still don't know what the growth, the prefactor for this growth rate was. So we calibrated that from data from one of the pins in this experiment, and then applied it to all of the other pins. And in doing that, we see we get a pretty good agreement for the maximum cladding wastage thickness as well as the cladding strain. And so this is very nice because that maximum thickness is one of the licensing criterion that's going to be used by the NRC in developing these. So we have a tool now that allows us to predict that fairly well. We don't do as well at lower heights in the we don't do as well at lower heights, and I think that likely is resulting from this growth exponent. So we've started some phase field work to try to address that. I don't really have time to go into that today, but it's something we're planning to work on for the future. So yeah, on this topic of metallic fuel. So again, here's a new fuel type where we don't have much data. We have some, but not enough for licensing. So we've used atomistic and mesoscale methods to try to answer a couple questions around swelling and fission gas release, as well as FCCI. And so we've resulted in a couple of models that have been put into Bison to use for a much broader range of metallic fuel designs. So some of those types of designs would be things like annular fuel, where they don't use bond sodium and the fuel more expands inwards. Also cladding interliners, which is something Ben and I are working on, where there's a diffusion barrier. So this type of model can be used much more effectively in those types of to extend to those new types of designs. So in the remaining time I have left, I'm going to talk a bit about some work that I worked closely with Ben on a few years ago on uranium silicide fuel. So uranium silicide fuel has been of interest as a accident tolerant alternative to UO2. This is because it's got it does have a lower melting temperature, but it has a much higher thermal conductivity. So that may give a better margin to melting temperature in an accident type scenario. So the fission gas release behavior of U3Si2 is not so well understood, but there's evidence from high temperature radiation that suggests that pellet form fuel would remain crystalline, unlike lower temperature uranium silicide, which generally amorphizes. So at higher temperatures, what evidence we have says it probably is more similar to UO2. The microstructure of the fission gas bubbles is similar to UO2. And so a Bison model was developed based on these assumptions a couple of years ago. And so when they developed that model, they did some parametric study to try to understand what are the biggest sources of uncertainty in this model. A couple of parameters that they found to be very important that could be kind of directly addressed through some atomistic calculations were the bubble dihedral angle and the surface energy. Those weren't available, but Ben and some collaborators developed a nice molecular dynamics interatomic potential to calculate those values, which could be used in Bison. So that's kind of one example where we can directly use atomistic data in Bison. But we also use that data to parameterize the Marmot model. And so where Marmot came in was looking at another parameter, which is also very important for fission gas release, which is this saturation coverage of grain faces. So what that parameter means is that we assume that fission gas bubbles grow on grain boundaries or grain faces, and they grow up to a certain fractional coverage. And at that fractional coverage, basically, they become completely interconnected and release all their gas. So there wasn't really a measured value available for that in uranium silicide. And so this initial effort in Bison used a theoretical estimate of 0.78, which is pi over 4, basically. So we knew from some previous phase field simulations that this grain boundary venting, this interconnection venting process was strongly dependent on a couple of parameters, such as the intergranular bubble area density and the dihedral angle. So we used some phase field simulations to determine that the goal was to use some phase field simulations to determine that fractional coverage at saturation, this Bison value with so much uncertainty associated with it. So to do that, we're using a more sophisticated phase field model. So some of the important physics that it captures are the grain boundary and surface energies. We can control those independently. We can look at multiple grains of the silicide fuel, unlike the Cahn-Hilliard model that I described before. We track vacancies and fission product species independently from each other. And then, yeah, so as far as setting the bulk energy and interfacial energy, we developed, this was a model that we developed a few years ago that allows us a lot of flexibility in parameterization. And so this is a model based on a grain potential functional. And so it's a multi-phase and multi-order parameter extension to a grain potential based phase field model that was originally developed by Plapp a few years ago. So some of the advantages of this model, like I said, we can separately control the bulk energy and the interfacial energy, which allows us greater flexibility in controlling the surface energy and the grain boundary energy. Removing that or decoupling the interfacial energy from the bulk energy allows us to also independently control the interface thickness. So that allows us to use a coarser mesh, which gives us improved computational performance. It's similar to a different phase field model known as Kim-Kim-Suzuki, but it's a little more efficient numerically than that. And it also prevents the spurious formation of additional phases at two-phase interfaces, which is something that's plagued a lot of multi-phase field models in the past. And so this is a topic I really enjoy, but we're getting a little short on time, so I probably should, I'm happy to talk more about that to other folks. Talk more about that later, but try to get to the upshot, which is the results of the phase field simulations. To parameterize them, we used some data that were done, data that was based on rate theory calculations performed by collaborators at Argonne National Lab. So they did rate theory simulations to help us get a good idea of the initial concentration of bubbles on the grain boundary, because as I said before, some previous work we had done showed that that is likely important. So the initial conditions, yeah, based on that initial number density, we looked at kind of a representative size grain boundary, and then ran simulations of growth and interconnection, which you see there. So you start to see, you know, in that first snapshot, just a few bubbles have interconnected. The second one, pretty much all of them have interconnected at this point, except for a few. And then in that last snapshot, basically every bubble is interconnected. So in order to kind of bring that into the Bison model, you know, we can look at a lot of the statistics of those bubbles, you know, as growth occurs. But we thought the most relevant thing to do is to try to compare what we saw from these simulations to what Bison's assuming. So to do that, we plotted out on the x-axis is how much of the grain boundary is covered by bubbles, and on the y-axis is what fraction of bubbles is vented to the grain boundary. So Bison was assuming it shoots up straight to from 0 to 1 at a value of 0.8 pi/4. We see in reality that it's a much more gradual curve. But to kind of try to give something that's useful for the current Bison model, we said, okay, well, let's say we can calculate this with the phase field simulations just at the point where the SE stat, we're going to set that to the point where the slope of this curve is the greatest. And then so we did that for several different bubble initial configurations. So, you know, 5 is not a great number for statistics. We'd like to do more, but these are relatively expensive. And so this does at least give us some idea of the amount of variation that's happening. The variation is not that high. So we calculated a mean value of 0.6, which was quite a lot smaller than that value of 0.78 that we were initially using. And then we also have the standard deviation, which can give us some idea of the uncertainty in this value. And so we looked at a couple different, we looked at the effect of a couple different assumptions we were making in the simulations, such as what is the shape of this grain boundary. I don't have time to talk in great detail about all the other things that we looked at. This is just to kind of give one example showing that assumption that we made didn't have a strong impact on the value that we found. So to tie this to what the field performance community really cares about, I wanted to show how this information was used in Bison. So the plot on the top right was the uncertainty associated with the initial range of that parameter FCSAT. We did some new simulations looking at an actual irradiation in the advanced test reactor using our newly narrowed range of uncertainty in FCSAT. And so if you look at the size, so this is not a complete apples to apples comparison, but I think it does give you a sense that we've reduced the uncertainty associated with that parameter quite a lot. And we also, it's not shown here, but the performance of the model is really significantly improved. Look, having a value of FCSAT at 0.78 caused tremendous problems for the model to perform model's performance, because the fuel just swelled way more than it would physically. So this also brings us more in line with what should happen physically, and that actually made the model perform quite a bit better. So that is the conclusion for this section. I mean, again, I think we've shown we have a range of atomistic to mesoscale to engineering scale. And by combining all these different methodologies, we can reduce the uncertainty associated with the calculations, and also provide a tool for fuel designers and analysts that can be useful in developing new types of reactors and licensing new designs. So with that, I'd like to thank you very much for your attention. Just show a picture there of the folks that I work with that help make a lot of this work possible. So I want to thank them, and also thanks to the DOE NEAMS program for funding support for most of this work. So with that, thanks again for coming and your attention, and I'm happy to take any questions.
All right, do we have any questions? We'll start in the room and then we'll call on and see if there are any. I got kind of a theoretical question. If you had engineered the metallic fuel with this porosity already there, would that virtually eliminate any kind of material evolution in terms of its spatial distribution with burning?
That's a really good question. I mean, so there are ways to try to produce metallic fuel with powder. So as we were talking about, using like a more of like a sintering type technique could allow that built-in porosity to form. And yeah, that maybe could allow some of that fission gas release to happen earlier. I think that the downside with that would be that you'd lose like the uranium density and you'd lose the fission density, but you end up losing that anyways as the fuel. So usually what they do is they cast the fuel pin and they leave about, I think it's only about 75% of the radius of the cladding, because they know so much of that swelling is gonna occur. So yeah, eventually they lose that uranium density effectively. So yeah, very interesting question. I mean, I don't know that anyone has tried that before, but I think there are ways that could be done.
Other questions?
I have two questions.
Mhm.
Where do we stand with the documentation of the peace field plot? So out of most, field lack documentation, and even like examples.
Yeah, so we do have a we do have a documentation page that does have some of the main subsystems and some of the theory explained. But yeah, I think that the problem is NEAMS doesn't have as much interest in funding us to do user documentation as Bison. So So I think you find like the documentation in Bison is better than what we have for face field environment, because they have a lot more industrial end users that care about Bison than about the Mesa scale tools. So they're more willing to spend money on people adding to the documentation. So for us, we kind of do it as like when we have time, but we don't usually unfortunately get funding directly to work on documentation. So hopefully the goal is to kind of try to keep letting NEAMs know, like show all these examples that we have of this multi-scale approach, how we've been able to be successful, and so that they can see more and more value of that Mesa scale work, and hopefully we can convince them more. But also it's good for me to know when people are interested in using it, because then I can tell the program leadership like, hey, we have people interested in this code, but like the lack of documentation is an impediment. So how about some money?
So the second question, if we compare like the new scale models in the piece field, open source code and Marmot, so how do they compare apart from that Marmot is specific for nuclear materials, like for grain growth, the model in piece field and Marmot, which one?
So the difference would be like the model would be the same. The difference would be that like Marmot would have specific values for the grain boundary energy and grain boundary mobility in UO2, whereas like the base grain growth model in Moose face field is like for copper. So it's a difference of like, is it a UO2 specific parameter, then it should be in Marmot. If it's kind of like a generic material property that you could, find in the literature easily, that should go in Moose face field. In reality, a lot of the data that's in Marmot is actually in the literature. It's just a matter of like taking the time to look it up. So there is actually a push, particularly by Derek Gaston, who was basically the guy that created Moose. Like he's really pushing to have all of these applications as open source. Bison, Marmot, Griffin for neutronics. I mean, he really wants to open source everything. Because yeah, like I said, in reality, a lot of the data that is in the literature already, it's just a matter of like taking the time to look it up. So there isn't a lot that's like truly proprietary. I don't think. At least not.
Yeah, as a related comment on top of that, are there functions or models that are restricted to Marmot or to Bison that are not available in Moose? Because that's maybe as important as the parameters themselves.
I think like there are a few like things like we have a model for restructuring, which basically says okay, the dislocation density inside a grain builds up at this rate based on fission density. And then we introduce new recrystallized nuclei as a function of that dislocation density. So like that, some of the model parts that are needed to capture that are not in this phase field. But I mean, I think that's a pretty specific. And then like, I think you worked on, when you were at INL, some of the free energy models, right? Yeah. So that is like, again, those are things that are in the literature. It's just a matter of like taking the time to actually, write them in code. So yeah, that is a model that's in Marmot, but not in Moose. But I think like, yeah, you could code it up pretty easily. It's not like someone went and did a whole bunch of experiments just to get us something.
Yeah. Other question.
I think it may have been slide 16, but could you, I heard that Dakota optimization was a technique used to fit some data. And I just wasn't familiar with that. Is that like a tool within Moose? Is that?
No, Dakota is actually a code developed at Sandia National Labs. So it is kind of an interface to, I should say I've never used it myself. That work was done by my former colleague Al, but yeah, that's one. I think it's open source actually.
Yeah, it is. So now they're implementing a lot of different Moose stochastic tools as well.
Yeah,
getting a lot of that functionality. Other questions, comments?
anyone. Let me check if we got anybody online. I haven't seen it. Nope, nothing in the chat, so anybody else here then? Last year. All right, thank you, Larry.